Alright, in this video we're taking a look at the first type of pH titration problems. It's the most straightforward one where there's a strong acid being titrated with a strong base. In this problem we've got 50 milliliters of 0.100 molarity nitric acid, and nitric acid's a strong acid, has a large Ka value. That's going to be in a beaker. It's being titrated with 0.100 molar barium hydroxide solution. You remember whenever you have a metal hydroxide, you're dealing with a strong base. Now this strong base is a little bit unusual in that it's got two hydroxides in its formula. That's going to be important. We remember that strong acids and strong bases completely ionize in water, so they're completely dissociated into their ions. We're going to calculate the pH during the titration at various points, and that's why it's called a pH titration problem. A typical acid-base titration problem, you're just trying to standardize a base or figure out what volume is required to reach the equivalence point. So it's basically a stoichiometry question. In a pH titration, you're actually finding the pH at various points in the titration, up to the equivalence point and beyond the equivalence point. So let's jump in. If you think you know what you're doing, you can pause the video and you can try this yourself. Otherwise, go along with me. So we're going to start with 0 milliliters of base have been added. So part A, 0 milliliters of barium hydroxide have been added. If we've added no barium hydroxide, then really we're just finding the pH of the nitric acid solution. So we have 0.100 molar nitric acid sitting in our beaker, and we just want to find out the pH of the solution. Well, nitric acid is a strong acid, so it's completely ionized. If you want, you could write an equation. Nitric acid reacts with water, completely ionizing to make hydronium and nitrate ions. Now you have 0.1 molar nitric acid. The water is a liquid in this reaction, so we can ignore it. There is some hydronium in pure water, but it's so small to begin with, 1 times 10 to the minus 7 molarity, that we just ignore it. In pure water, initially, there is no nitrate. So the nitric acid is dissolved in water. We're assuming these are 0 initially. Since the nitric acid is a strong acid, it dissociates completely. It ionizes completely, so it loses everything. The ratio in the balanced equation is 1 to 1 to 1, so we end up with no nitric acid, 0.1 molar hydronium, and 0.1 molar nitrate. Since we know the hydronium concentration, 0.1 molar, we can say the pH is the negative log of the hydronium concentration, which is negative log of 0.100. If you grab a calculator and do that, or do some mental math, this is 10 to the minus 1, so the pH will be 1.000. And note on significant digits, if you have 3 significant digits like this in the concentration, you have 1.0. The pH here 1.000. Now let's start titrating. We're going to add 10 milliliters of the barium hydroxide. 10 mils of barium hydroxide. Now notice that the barium hydroxide has 2 hydroxides in its formula. If it dissolves in water, you get 1 mole of barium ions for every mole of barium hydroxide. You'll get 2 moles of hydroxide ions. So if we had a 0.1 molar solution, that's what the question said, of barium hydroxide, we're going to end up a strong base. It ionizes completely, so we end up getting 0.2 molar, okay, 2 to 1 ratio, so twice as much, 0.2 molar hydroxide ions. So this is what we're really adding. We're adding 0.2 molar hydroxide. So we've added 10 milliliters with 0.2 molar hydroxide ions. What's the net reaction that's happening here? Well, we could, if we want, write a reaction between barium hydroxide and nitric acid, HNO3. But that would be a molecular equation. There's an easier way to do that, and that's to write the net ionic equation. We remember that nitric acid is completely ionized, and so that it really has hydronium ions and nitrate ions. And the hydronium ions are the part that we're interested in as the strong acid. Those hydronium ions from nitric acid will react with hydroxide ions from the strong base. So whenever you have a strong acid and a strong base, you don't need to write their molecular formulas. You can just represent the strong acid as hydronium and the strong base as hydroxide. And then what you produce, in this case, would be 2 water molecules. Now some people, instead of hydronium, they would prefer to say just hydrogen ions. So you could say hydrogen ions come from the strong acid, reacts with hydroxide ions from the strong base, and that produces 1 water molecule. It doesn't really matter which way you do this. Either way, we get a 1-to-1 ratio between the hydronium and hydroxide, or the hydrogen ion and hydroxide. All right, so I'm going to, for this video, I'm going to use the hydronium ion representation. Now this, if you stop and think about it, is the reverse of the Kw reaction. This is the reverse of the self-ionization of water. Since it's the reverse of that equation, its Kc value is 1 over the Kw value, which means it is a very large equilibrium constant. That's important because it means the reaction will essentially be complete. Now, because we're mixing solutions, we're adding 10 milliliters of barium hydroxide to 50 milliliters of nitric acid. Remember the question said we had 50 milliliters of 0.1 molar nitric acid, and we're adding 10 milliliters of 0.1 molar barium hydroxide to that. I don't want to have to worry about dilution effects, mixing 10 mils with 50 mils to get 60 mils total. I don't want to have to worry about diluting. So what I'm going to do is I'm going to use in my ice table here, instead of the usual molarities, I'm going to use moles, and in fact I'm going to use millimoles. You remember that moles can be calculated by taking concentration and multiplying by volume. So if we took the 0.1 molarity and multiplied by 0.05 liters, 50 milliliters, we'd have the number of moles of nitric acid that was originally present. But if I leave the volume as 50 milliliters instead of converting to liters, then instead of moles, I'll be getting millimoles. So if we use milliliters in the volume, we'll get millimoles instead of moles. So for the strong acid, 50 milliliters, 0.1 molarity, if you multiply those two numbers, you'll get 5.00 millimoles of hydronium initially. That's what was in there initially from the nitric acid. What about the hydroxide? Well, we've added 10 milliliters, and although the barium hydroxide concentration was 0.1 molar, the hydroxide concentration is actually 0.2 molar. Okay, keep that in mind. So when I do C times V, I'm going to do 0.2 molar times 10 milliliters, and that'll give me 2 millimoles of hydroxide. Since water is a liquid, we can ignore it in our ice table. We know that this reaction has a large Kc value, so one of these two things will get used up. In a 1-to-1 ratio, the limiting reagent will be the smaller number. So minus 2, we have 3 millimoles and 0 millimoles, like that. So now what we want to do to find the pH is find the concentration of the hydronium. We take the moles, or the millimoles, and we divide by the volume. So if we have 3 millimoles, we'll divide by the total volume now in the titration, but we're going to leave the volume in milliliters because we're using millimoles. So if we had 10 milliliters, and we originally had 50 milliliters of acid, then the total volume is now 60 milliliters. So 3 divided by 60 is going to be 0.0500 molarity. So there's the concentration of hydronium, and now your pH is the negative log of that. So negative log of 0.05 is 1.301. Okay, so the pH went from 1 to 1.301 when we added some base. So now let's add 20 milliliters of base. If you think you understand what you're doing, pause the video and try setting it up yourself. So the reaction is the same as before. We have hydronium ions from the strong acid reacting with hydroxide ions from the strong base, producing water. We had 50 milliliters of 0.1 molar strong acid, so we had 5 millimoles of hydronium, and we had now 20 milliliters of 0.2 molar hydroxide ions, and so we have 4 millimoles of hydroxide. We can tell that we're still before the equivalence point because we've got more hydronium in the beaker than the base that we've added. So this must still be before the equivalence point. So now we'll lose all of this, -4, and we've got some leftover hydronium. So again, evidence that we are still before the equivalence point. So now we can say the concentration of the hydronium, moles over liters, or millimoles over milliliters, 1 millimole over the total volume now would be the original 50 milliliters plus this 20 milliliters, so we have 70 milliliters in there now. So 0.1 divided by 70 is going to be 0.0143 molarity. And the pH will be the negative log of the hydronium concentration. It's gone up to 1.845. So our pH, as we keep adding base, is slowly rising. Now if you were watching this on a graph, volume of barium hydroxide added and pH, what would we see? Well, the pH would have started at 1, and that's when we had 0 milliliters of base added. We've added 10, 20 milliliters, and our pH has risen from 1 to not even 2. So the graph is looking something like this. It's looking almost flat. Okay? That's characteristic of a strong acid, strong base titration curve. So we're going to do the third one now. We're 25 milliliters of base, and you're going to see here that this is a more interesting point in the titration. So 25 milliliters of barium hydroxide. So the reaction is still the strong acid, represented as hydronium, plus the strong base, represented as hydroxide, makes water. We had 5 millimoles of acid, 50 milliliters of 0.1 molarity. The hydroxide is now 25 times 0.2. It's going to be 5 millimoles also. And there's the clue, if you didn't notice it on the numbers earlier. This is now the equivalence point because we've got equal numbers here, an equal ratio, 1-to-1 ratio of hydronium and hydroxide. So this loses 5 millimoles, this loses 5 millimoles. We have nothing left. In fact, all we have left is pure water. So we have only pure water remains. There's no excess hydronium, there's no excess hydroxide, there's just pure water. If we assume the temperature is 25 degrees Celsius, the pH, and we could show this by calculation using the kW, but we'll just do it as a fact. The pH of pure water at 25 degrees Celsius is 7. Okay, so there is our pH value at the equivalence point. And that's important because you'll notice that in this titration, if we look back at the molecular equation for a minute, we had nitric acid. It was reacting with barium hydroxide. There's 2 OHs and only 1 H, so I'll put a 2 here to balance the H's and the OHs. That would produce water, 2 water molecules, and barium nitrate. So in reaching the equivalence point, all that we have in our beaker at this point is water and this salt, barium nitrate. There's no leftover nitric acid, there's no excess barium hydroxide, there's water and salt. And this salt, barium nitrate, if you stop and think about it, you'll realize it's a neutral salt. The barium cation does not affect pH, and the nitrate anion, although it is a conjugate base, it's the conjugate base of a strong acid. And we know that the conjugate base of strong acids is so weak that it essentially does not affect pH. So the pH at the equivalence point for any strong acid, strong base titration will be neutral. And that's because the salt produced at this reaction is a neutral salt. Okay, the cation will come from the strong base. That will not affect pH. And the anion will come from the strong acid, and therefore it will always be too weak of a conjugate base to affect pH. So for strong acid, strong base titrations, we always get an equivalence point pH of 7. And we always see this dramatic jump in pH like this. So the equivalence point pH is always going to be 7 for a strong acid, strong base titration. Now we're expecting the pH will go like this, and then we'll level off again when we continue adding strong base. So let's check that. We're going to add 30 mils of strong base. Okay, see there's a little bit of a typo here. We're not going to go back and add 15. So we're going to do 30 and then 35 mils. So part E, 30 milliliters of barium hydroxide. Now in a normal acid-base titration, you stop at the equivalence point. You want your end point to be the same as the equivalence point. In a pH titration, we deliberately go past the equivalence point to create that full graph. So we'll have the same balanced equation. Hydronium reacts with hydroxide to make water. We had 5 millimoles of hydronium. The hydroxide was 0.2 molar. Remember that 2 times 0.1 is 0.2 molar. 30 milliliters means we've now added 6 millimoles of hydroxide. And since we've added more hydroxide than hydronium in this 1-to-1 ratio, we can tell we're past the equivalence point. So now minus 5, smaller number, minus 5. We're going to have some excess hydroxide ions in the water, in the beaker. So the pH is now going to be basic. So if we calculate the concentration of hydroxide, we have 1 millimole over the original 50 milliliters plus this 30 milliliters is now 80 milliliters. So that's going to be 0.0125 molarity. So now we can say the pOH is the negative logarithm of the hydroxide concentration, negative logarithm of 0.0125. So the pOH is 1.903, and that means our pH is 14, the pKw, minus the pOH, which is 14 minus 1.903. We get a pH, as expected, that's high, above 7. It's 12.097. So the pH, when we go past the equivalence point to 30 mils, 12.097. So the pH has jumped from very low pH at the beginning of the titration, slowly rising, and then a sudden sharp jump in pH, and now we're past the equivalence point and we're going to be on this plateau over here as well. In a strong acid, strong base titration, there is no buffering. Okay? The pH is slow to rise here and it's slow to rise here, simply because the concentration of hydronium is not changing very much as we keep adding base. But there is no buffering here. The equivalence point pH is 7, and then we have this characteristic flat initial portion, very sharp rise in pH, and a flat final portion to the graph. Let's do the last point in the titration. We're going to add 35 milliliters of the base, and we're expecting, if I was right, to see the pH plateauing. So it's going to be a little bit higher than this, but not much. So we'll have the same reaction. We're now adding 35 milliliters of barium hydroxide. So we had 5 millimoles of hydronium from the original acid, and now we've added 7 millimoles of hydroxide, 35 times 0.2. So now minus 5, minus 5. We have 2 millimoles of hydroxide remaining. Now there's more hydroxide here than there was before. The volume is a little bit higher as well. So the concentration of hydroxide is 2 millimoles over the total volume now is the original 50 plus the 35, 85 milliliters. And so we'll get 2 divided by 85, 0.0235 molarity hydroxide ion. Now, in the earlier point, we had 0.0125 molar hydroxide. Now we have 0.0235, almost twice as much. But remember, to cause the pH to rise by 1 unit, we would need the hydronium to drop by 1 unit, and that would happen if the hydroxide increased by 10, a factor of 10. So this doubling of hydroxide concentration really isn't going to cause a dramatic increase in the pH. We'd have to increase hydroxide by a factor of 10 to cause a pH rise of 1 unit. So this is going to increase the pH, but not dramatically. So the pOH is the negative log of this number. I'm running out of room here, so I'm just going to be a little bit lazy. Negative log 0.0235, 1.629. And my pH will be 14 minus the pOH, 12.371. So coming back to our original question sheet, the pH after 35 milliliters, 12.371. Alright, so we're seeing again the strong acid, strong base titration, a very slow, steady rise in pH, followed by a very sharp rise in pH when you reach the equivalence point, and then a slow plateau here again. The equivalence point is this point of inflection where the graph goes from being concave up to being concave down like this. It's the point, roughly speaking, the midpoint of this rise in pH like that. Okay, there's a more precise way to describe the equivalence point graphically, but that's not a bad way to do it. In a strong acid, strong base titration, that'll always be pH 7. Now, because of this very sharp rise in pH, you actually have quite a possibility in terms of a range of acid-base indicators if you wanted to select an indicator for this titration. Theoretically, you'd want an indicator whose pKa value is close to 7. The best thing to do is to choose an indicator where the pKa value for the indicator is close to the pH at your equivalence point. But if you have such a sharp rise in pH like this, really then you could choose an indicator that changes color anywhere in this range of pH values. So an indicator that changes color anywhere probably from pH 3-ish all the way up to pH 9 or even 10 up here would probably be a sufficient indicator for this titration, because although the color change would occur at the wrong pH value, that would represent almost no difference in the volume of base added because of that sharp rise in pH. So for example, if we were doing this in our lab, we would probably use phenolphthalein as an indicator, which changes color not at pH 7, but up at around pH 8.5, 9. Although that's higher than the equivalence point pH, that pH over here would represent almost no difference in the volume of base added. So therefore phenolphthalein would still be a good indicator for that titration. But the basic idea when choosing an indicator, choose an indicator, if possible, where the pKa of the indicator is close to the pH at your equivalence point. That'll mean that the indicator changes color right near that pH value. So there you have it, pH titrations for strong acids with strong bases. There was no buffering at any point in this titration question, and it always left either excess hydronium or excess hydroxide, and that led to pretty easy pH calculations.